part 3. You've made it to the end. We're so close. So let's get started. We're going to be talking today about part 3 of electromagnetic radiation, which is other types of spectroscopy. So we've talked about a little bit about introduction to waves. We've talked about line emission spectrums, and then we're going to talk about our other types of spectroscopy techniques. We will continue to talk about these in reference to other things, but we're going to kind of wrap things up with this light and energy. And I promise, if you say to yourself, where's the stoichiometry? We are going to get to that sooner than later, okay? All right. So, like we've talked about before, scientists can take radiation and kind of poke around to see what's going on inside different atoms. You can also use magnets, you can use electricity, and then take the electromagnetic radiation that comes off of those atoms and take a look at them. But once scientists kind of figured out that there was more going on inside the atom than they anticipated, what they ended up doing was they started to kind of poke around with a bunch of different types of spectroscopies. And you are going to not have to be able to identify or read these spectrums that are produced by these techniques, but you should kind of know what they do and be able to do calculations with them. And like I said, we are going to be actually moving into electron configuration next, and we will be analyzing some of those spectrums in our next lesson. So there are a bunch of different kinds of spectroscopy, and depending on the intensity of the particular spectroscopy technique, it can do more or less. So if you kind of remember from our initial lecture, we talked about microwaves being kind of really long waves with pretty low frequencies. They, all things considered, have really low energies. And when we talk about energies increasing, microwaves are the lowest, then we have radio waves, then we have infrared, then our visible light, ultraviolet light, X-rays, and gamma rays in terms of their intensity and their danger to you. Realistically, anything that's ultraviolet or higher has the potential to do damage to human tissue, so you've got to be careful. And that's what causes like a sunburn when you're outside. So if you get hit by ultraviolet light, that is, your skin is not protected against that, and so you end up getting a sunburn from that. There are 3 kinds of ultraviolet light. This is kind of a tangent, but that's okay. There's ultraviolet A, B, and C. And actually, ultraviolet C is intense enough to kill and cause bacteria to not transfer, and it cleans things out. So like in our goggle cabinets, we keep our goggles in those cabinets. It actually has an ultraviolet C light bulb in there, and when we run it, it kills any bacteria or pathogens on there that could potentially make you sick. So that's kind of the idea behind that. So anyways, if you think about energy, when we talk about the different types of spectroscopy, the higher the energy that you see, the more stuff it can do to a particular atom. So if we talk about kind of our lowest energy one, it's microwave spectroscopy. Microwave spectroscopy, what it does is if you bombard a sample with microwaves, what it does is it causes the molecule to spin. Okay? So literally it's like, hey, I'm going to hit this with microwaves, and it goes, woo, and it spins. And when you use a microwave to heat something up, it actually causes the molecules to move and vibrate, and that's how they heat up. So when we talk about microwave spectroscopy, it causes molecular rotation. And as a consequence of that, you can actually, looking at how the molecules rotate, you can actually use that to determine how long a bond is. So from the center of one atom to the center of the atom it's bonded to. The next highest electromagnetic radiation that you can use is something called IR, or infrared spectroscopy. So what IR does is it causes molecular vibrations. So it causes a stretch within the bond. So if you think about it, it's not just like spinning the molecule, it's actually making a bond stretch and flex. And depending on the different frequencies that you get the stretch happening at, you can actually tell the types of bonds in a compound. So like a carbon connected to a carbon will stretch at a different frequency than a carbon connected to an oxygen. And there's this huge catalog of different things that can actually be figured out based on where those stretches happen for infrared spectroscopy. If you get into analytical chemistry, you use it a ton. It's cool. You make little pellets and you put it into a machine, and it's generally kind of cool. Another type of spectroscopy is called UV vis spectroscopy. So UV is ultraviolet, vis is visible light. So what UV vis does is it uses visible light, the wavelengths that are associated with visible light, as well as ultraviolet light, which is called UV vis spectroscopy. And what ends up happening is ultraviolet light and some of the visible lights are actually high enough in energy that you can actually bombard a sample with it, and it causes an electron transition. And that's kind of like what we saw with the electrical current running through those samples. So it'll cause electrons to jump and fall back down. And then it can give us a couple pieces of information about it. It can be used to determine the structure of a particular compound. And actually, if you guys have used our Spec 20s, with the molarity last year, if you remember, if you used the Spec 20 before, you can use that to determine solution concentration. So we shoot a sample of radiation through that particular, through a particular cuvette, if you remember the term, and then it'll tell us how much of the light gets through the sample, and then we can figure out the molarity of a particular solution, which is kind of cool. And then the last one, my face is kind of in the way, but it's called X-ray / UV PES, and PES stands for photoelectron spectroscopy. And that's the one that we are going to actually be paying attention to when we get talking about electron configuration. It's probably, honestly, the most useful one in terms of helping us know more about the insides of the atoms, because what happens is when you bombard the sample, it actually, you use either ultraviolet light at a high energy or you use X-rays. And when you apply that much energy to the sample, it actually flicks off electrons from your element. And so what it does is it tells you how many electrons it flicked off. It tells you how much energy it took. And it actually is the thing that leads us to figure out electron configuration, which is pretty slick. So we will be talking about that next. And then electron configuration is coming, which is everybody's favorite. So what we're going to be doing is 2 more types of calculations. They're kind of similar to the ones that we did yesterday, but they're just applied to a spectroscopy context, and we'll see how it goes. So here's example 1 from unit 1C. Ultraviolet light with a wavelength of 92 nanometers can remove the 3p electrons of aluminum. And I know this because I looked up the data for you. How much energy is needed to remove 1 3p electron from aluminum? And then here's the second part. How much energy for 1 mole of 3p electrons? When you look at the energy for 1, it doesn't seem like that much. But if you think about 1 individual electron, it's not that much. A mole of electrons is a different story. Here is example 2. In the stratosphere, UV radiation can break down a pollutant called a CFC, which stands for chlorofluorocarbon. UV radiation breaks the C to Cl bond. It's a very high intensity electromagnetic radiation, like I talked about. It takes 542 kilojoules to break 1 mole of C to Cl bonds. So remember, kilo, there are 1,000 joules in 1 kilojoule. Okay, just keep that locked up here. What is the wavelength of the radiation needed to break 1 C to Cl bond? So again, pay attention. It takes 542 kilojoules to break a mole of bonds. I want you to tell me how much energy it takes to break 1 bond, okay? So try those on your own, then pop into my video to kind of get the answer, and then go from there and get help if you need to, all right? Good luck.